This lesson is on degrees and radians. This is part 2, following up from part 1 of degrees and radians. Both of these are from 4-2 in your book. This lesson is specifically on linear and angular speed and the area of a sector. Last time we talked about decimal degree form, radian measure, radian degree conversions, coterminal angles, and arc length. So now we're going to be talking about the linear and angular speed and area of a sector. So linear and angular speed. We know the equation dirt, or D, equals RT from algebra, which means distance equals rate times time. We can manipulate this equation in terms of rate. If we wanted to rewrite this same dirt equation in terms of rate, we would get R equals D over T, which means our rate is equal to some distance divided by some time. We know this more generically when we talk about driving, for example. You drive a certain amount of miles and a certain amount of hours, you get your speed equals miles per hour. We know we talk about the distance divided by the time. So in linear and angular speed, it works the same way. The distance that we have on a linear speed is the arc length. So that is, if we took this circle right here and we undid it, we just took whatever this slice was and we put it in a straight line. That means we're traveling some distance. That distance is that S. If you can think about, we walk on the planet of the Earth, not proportional obviously, and I'm just going some distance, even though the fact that I'm walking on a circular object. So we give our linear speed as V equals S, our arc length, over whatever time it took to do that. We can also talk about speed in terms of angles. So instead of talking about a distance that you walked, we can talk about how many rotations, or more generically, the angle that you walked. So omega, this W looking thing, omega, is equal to theta, or our angle, divided by our time. So that gives us an angular speed when we take our angle divided by our time. So let's do an example. Find the angular speed of the disk shown in radians per second if the disk rotates at a rate of 3.5 revolutions per second. So the first thing to note is revolutions are not the same as radians. We're saying we went around 3.5 whole times. So we know we're going to have to convert that. We haven't dealt with anything with revolutions yet, but we know how to convert that. So the question says, find the linear speed of the disk if it begins to rotate at a rate of 3 revolutions per second. So the angular speed that we're finding is omega equals theta over t. So we went 3.5 revolutions. The amount of radians per revolution is 2 pi radians per 1 revolution. We know that there's 2 pi radians in every single revolution, or every single time you go around that circle. And we went around in 1 second. So we had a rate of 3.5 revolutions per second. If we were trying to find the angular speed, which is part 1, we say 3.5 revolutions times 2 pi radians per revolution divided by 1 second, and we get 7 pi radians per second. That's my angular speed. If we wanted to talk about linear speed, and we said that find the linear speed of the disk if it begins to rotate at a rate of 3 revolutions per second, we're given this disk that's 120 millimeters in diameter. So we can change that to a radius of 60 millimeters. Well, the only equation we know for linear speed so far is V equals S over T. V equals arc length over time. We know that arc length is equal to R times theta. S equals R theta. Or when we were trying to find theta before, we knew it was theta equals S over R. We can rewrite that as S equals R theta. So we can rewrite our linear speed equation in terms of R and theta, since we don't know S. And we get R theta divided by T. That gives us an equation of 60 millimeters times 3 revolutions times 2 pi radians per 1 revolution, all divided by 1 second. We're doing each of these things per second. That means your time is 1 second. We end up with 1130.97 millimeters per second, and that's approximately 67.9 meters per minute. Okay, let's move on to an area of a sector. So a sector is defined as a region bounded by a central angle and its intercepted arc. I don't know if that makes sense to any of you. Let's talk about it in terms of food. I like that better. So a sector is like a piece of pie. The size of that piece of pie depends on a lot of things that are obvious, right? How wide or skinny that piece is, which we talk about in terms of angles. which would be theta in this case, how big each side of the piece is. So if we have a piece of pie that is, the size of your hand versus a piece of pie that is the size of your table, that's going to affect how big each side of that pie is, which is our radius. We know that as our radius. And how big the crust is, which is S. So we want to know that full size again. R and S are related by theta, obviously. And I only bake 2D pies, so we're not really worried about the height right now. So when we find the area of a sector, we are finding the area of that piece of pie. That's what we're looking for. And the quantities of the piece are proportional to the quantities of the whole. If we looked at an area of a piece of pie, or an area of a sector, or an area of a piece, divided by the area of a whole, that's going to be proportional to the length of that crust for that piece, the length of that arc length, divided by the length of the crust for the whole pie. Those things are going to be proportional to each other. So more generically, we can talk about this in sectors and circles. The area of a sector divided by the area of a circle is going to equal the arc length divided by the circumference. Well, we know some of these things. We know that area of a sector we'll just call A for now, area, and divided by the area of a circle, which is pi r squared, is equal to r theta, our arc length, divided by 2 pi r. We can write this more generically by doing some cross multiplication as area equals 1/2 r squared theta, or I like to remember this as 1/2 theta r squared. Sounds a little bit more like pi r squared, and with the 1/2 theta r squared, let's plug in something we know. What if we had a full rotation? What if we had a full pi? What if our theta was equal to 2 pi? Well, this equation would then become 1/2 2 pi r squared. This area of a sector would become 1/2 2 pi r squared. Well, we can cancel out that 2, and we're ending with pi r squared, which makes sense. If we have a theta equal to 2 pi, the area should be the whole circle. So let's find the area. Let's do an example. Let's find the area of a sector of a circle with the given central angle theta and a radius r. So we're given theta equals 3 pi over 4 and r equals 1.5 feet, and we're asked to find the area of that sector. We apply the equation 1/2 theta r squared. We can plug in theta equals 3 pi over 4 and r equals 1.5, and we can solve and get area equals 2.65 feet squared. That's how you find the area of a sector.